Vikram Sreekanti is my colleague at Berkeley. We'll be talking today about grounding big data. I wanted to set context. Many of you know this context, but just to kind of get us going on the right conversation. You know, in the past, we had these wonderful things in our organizations called the database. And it wasn't just a bucket of bits. The database actually came with some sort of model, right? It came with a relational model, but also often a business model of what was being captured in that database. And we're all familiar with this. And we had all this great terminology that we used to talk about the kinds of things in our database. It was a data warehouse. It was a single source of truth. And we had an enterprise information architecture to think about how this database would get populated and managed. And we often would talk about things like the golden master of our data. And there was a lot of organizational process and design around these concepts, all of which kind of led to the idea that really what we were trying to capture was the truth, capital T. Right? And IT managed this, and part of the issue here was that if you want to be the keepers of the truth, you'd better be careful about it. So, right, you would have people in IT who would sort of keep the truth sacred. They would make sure that things didn't go in there that shouldn't go in there, and it was all carefully managed. And in some of the leaders in this area would say things like, there's no point in bringing data into the data warehouse environment without integrating it. So very top-down design, very managed. And we all remember this past, and it feels a little archaic to us now. But I wanted to lay it out there because, of course, this is Strata Hadoop, where we talk about big data. And big data took us to a very different world, right? And whether that world was big or not so big is something people like to debate about, but it's definitely different, right? There were changes in volume and velocity and variety, those things that people like to call out about what's different with big data. And they were challenging, and there's been a lot of neat technology that's been developed to address those issues. But at some level, that's not the change we see from the previous slide. The change we see from the previous slide and the real challenge that we face as a community today is the meaning and the value of data has shifted and now depend critically on context. And so today I'm going to talk a lot about context, and Vikram's going to talk more, and give you a sense of what we mean. But to me, this is the fundamental shift that happened as we went through this big data ecosystem and change. So Ground is a system we're beginning to build. It's a research project and a set of services we're building at Berkeley. It's to give a broader context for big data. So I'm going to talk today about the motivation, really what's different. Let's zoom in more detail about what's changed in the way we think about data in the last decade. And then talk about putting big data into context. What do I mean by that? And then we'll talk more specifically about Ground as a services layer for data context. We'll actually show you some examples from our alpha implementation of how this kind of stuff can be useful. We'll also discuss other examples. And then I'll talk about some of the research challenges that my PhD students and I and our group at Berkeley are trying to tackle. Okay, so before I get too far into this, I know some of you are thinking, wait a second, hold out. Isn't this just metadata, right? And let's see. Well, what can I say? Metadata is the last thing anybody wants to work on, all right? And we see this in the Apache open source community. It is, in fact, the last thing that people did in the stack. People built storage engines and query engines and data movement pipelines. Just lately, people are like, maybe we should build some metadata stuff. It's literally the last thing people want to work on. But there's way more to data context than just metadata, okay? And also, what I want to impress upon you as we go through this talk is when you zoom out and you think about this bigger problem, it's not the last thing we want to work on. It's the final frontier, right? We did the easy stuff, all right? There's so much more to do. And this is really where we want to focus our energy in my research group, is really this final frontier of data context. Okay. So with that, let's talk about what's different. What's changed from that picture I had of the fortress and the guard? There's shifts from the top and shifts from the bottom. So from the top, there's real changes in the behavior of organizations working with data. Data-driven organizations today are very different than the IT organizations of the 1990s. And it's worth taking a little time and talking about that. Secondarily, there's been shifts in technology from the bottom up down to the very basic level of data representation. Okay? And we'll talk about that as well from the bottom up. So we'll look at both of these aspects to try to just pause and take into account what we probably already know about what's changed. So I may say nothing you don't know today, but perhaps this will get us focused on the right conversation. All right, so shift in behavior. If you look at data-driven organizations, take, for example, General Electric. They're building wind turbines, okay? And when you think about data in products like wind turbines, let's roll back a little and think about how data got into the product organizations to begin with. It happened with the internet. It happened with things like digital advertising, where suddenly there were organizations that were monetizing data. And their business units were deeply technical and were working quite a lot with data. And if you go to an organization that is monetizing data, you'll find that the groups that are working on that are not necessarily the IT services groups. Right? They're very different groups with different skill sets. They have data scientists embedded. They have business people embedded. It's not like the way that data was managed in the 1990s and early 2000s. And this has shifted from a few companies in Silicon Valley on the internet to lots and lots of companies. In fact, many companies that just build standard products. So the GE example more specifically is they build these wind turbines. And the wind turbines connect in mesh networks that share data about wind and then adjust the blades to account for what's going on. That tech stack of the data that's passing between these things, the predictions and the analytics that are going on with these physical artifacts would not be managed by IT. There's no way you would want, an IT person running that stack. That stack is run by the people who understand the product, right? And this happens to be a deeply technical product, but there's lots of other products where you'd say the same because the product people understand the customer and the use case and all those things. Right, so now we've got data that's being managed by product groups, by business units outside of IT. Marketing is obviously the most typical of these. And as you may know, Gartner predicted some years ago that by 2017, marketing would spend more on tech than IT does. It seems that that may be about right. All right? And again, in marketing, what's the difference? How did marketing get hold of the right to work with data in the first place? Well, marketing data actually isn't critical to running the numbers for revenue. It isn't critical to complying with government regulations. It's just data that, somebody in marketing might do something cute and figure out a way to make more money. Well, if you give smart people the license to do something cute and make more money, over time they become pretty useful to the business, right? They become way more useful to the business, in fact, than the guy who puts together the report at the end of the month. This is what generates business. And so there was an unstable equilibrium there where we're like, we'll let the marketing guys play with their silly data. That was not going to remain silly for long. They're actually doing creative things with the data. And they're going to generate ideas, and they're going to become the locus of energy for data in an organization. So marketing was this awesome canary in the coal mine for how business units were going to start to become the centers of gravity for their own data. Right? And in fact, Gartner's updated their predictions on this stuff. They now say by 2020, 90% of the IT budget will be controlled outside of IT. Sorry, 90% of, well, that's what it says. It probably should say tech budget. But 90% of the budget for tech will be controlled outside the IT organization. That's pretty phenomenal. So things have changed. And when things change this much, what happens is we have many more use cases for data. People are doing crazy and new things with data. Every day, we're inventing new stuff to do with it. There's now many constituencies, people who have different motivations and different compensation structures for working with this data. And so they have different incentives. And what this means is that data gets used in many different contexts now than it used to. Okay? And so the context, if you're the marketing department or you're the product group, you're going to have different interests and different knowledge and different understanding than people say in IT. So that was a sort of top-down view on what's different. Let's look at a bottom-up view. All right, where we used to have databases, we now have data lakes, right? Data lakes are full of not cooked fish, but raw fish, right? They're full of raw data, all right? And that raw data is good. We like raw data because it's easy to capture raw data, right? You can just dump your bits in the data lake. You don't have to go through a top-down ER diagram for your entire data warehouse before you can land a file. And it encourages exploration. It's all just bits, man. So anybody can go in there and they can get smart and they can do cool things, right? It's not been locked down in some sort of schema of truth with things that have weird names like business object data type format, right? Stuff like that. It's all very open to interpretation. So that's great. But what does any file in Hadoop really mean? It's a string of bits. It adopted the Unix notion of what data is, which is just literally a stream of bits. What any file means depends on the context in which you use it. It depends entirely on what you do with it. There's no definition of truth in the data lake. There's only bits. Okay, so let's go through a little scenario to illustrate this. It's not like these bits don't ever get interpreted. Obviously they do. So we have HDFS. It's full of cool stuff. In there, there's some file. It's a bucket of bits, all right? First thing to keep in mind is that actually this file does not live alone. It's part of a context. It might be, for instance, in a folder. So suppose that file was a day's worth of web logs. It's probably connected up in some sort of directory or hierarchy of a year's worth of web logs, which is really what we care about. And then we might take those web logs, and we might push them through a script. And that script is going to take the raw text of those web logs, and it's going to extract the entries in the web logs that represent orders for products, so actual purchases. So when you click on a certain thing with a certain kind of URL, that's a purchase. Right? So this script is going to pull out those lines of the web log, parse them, and turn them into structured rows representing purchases. And then that script will generate a bunch of files, which are purchase record files, and it will generate a schema, a metadata description, which it'll put in the Hive metastore, so that we can run queries in Hive or in Impala or one of those tools over those files and do analytics like market basket analysis. So we can do things like we used to do in the 90s that try to predict what things that people buy together that might surprise us. So it may be that people who rent the Sherlock series also read the Dora the Explorer series, which you might not have guessed. Okay. So you can do all that with that data. We started out with an Apache weblog, and now we've got market basket analysis over tabular data about orders. So that's one thing you could do with the data. Here's another thing you can do with the data, same weblog, all right? Here what we're going to do is we're going to push it through some code that extracts abandoned user sessions. So what's going to happen is we're going to go through the log, and we're going to construct sessions, which is multiple clicks from a single user within a window of time. And we're going to look for sessions that don't end in an order. So in fact, we're going to pull out almost the opposite data that we pulled out in our first model, okay? And we're going to take those things where you didn't buy something, and we're going to do what's called a retargeting model, which is we're going to figure out which of these things we should buy an ad on Facebook to try to get you to finish the deal. So this is something that showed up on my Facebook feed last week because I was shopping for a webcam, and I didn't ever purchase one. And lo and behold, Amazon was advertising webcams to me on Facebook, the very webcam I was considering buying. Right? And that comes through this retargeting model. Very nice, okay? But what happened here? Is that data file that we started with, is it something that generates a table of orders? Or is it something that generates sessions of things I didn't order? Right? Well, it depends on your use case. It depends on your perspective. These aren't even that different perspectives, right? These are both kind of marketing automation perspectives. But in general, in an organization, you'll get a kaleidoscope of views as to what a particular file or a particular bucket of bits means. Long way from where we started, where there's the database with the truth. Right? So from the bottom up, because of the technology stack, it's easy to have many scripts, many statistical models, many applications. So again, data gets used in many contexts. All right, which raises the question, how do we keep track of all this notion of like multiple realities and the context in which people work with data? This seems to be pretty important. And we don't have any tooling in the open source stack really to help us with it right now. Okay, so I say that the meaning and the value of these bits depends entirely these days on context. And there's three kinds of context I'd like to call out and we'll talk through. Application context, which includes views and models and code. Behavioral context of the people working with the data, so data lineage, data usage. And historical context, data and things in and over time. So let's start with application context. This is probably the thing you might most recognize as metadata. Okay? Models for interpreting the data for use in an application context. This includes traditional metadata on structure, so data structures. What are the rows? What are the columns? If it's a XML document, how is it nested up and what are the types? But tell me what's in this data and how I access it. Right? Traditional database data modeling. Secondarily, semantic structures, like what do the codes in this column mean? Where can I look up their meaning? How should I interpret the data that I store? And then recently also very typical to have statistical structures as well, like statistical models that you keep to do predictions and other things with this data. And if we're going to build a system like Ground to try to manage this stuff, a key issue here is that our metadata model, our meta model, has to be deeply unopinionated about what people think about context. It's much like internet protocols don't have opinions about the applications that run over them. That's why the internet can be used by everybody. We need metadata meta models here that are unopinionated. They can't be the relational model or XML or any other religion you ascribe to in the past, because those religious adherents need to come together in this place and be able to store what they want to store. Okay, so we want a very unopinionated model of this kind of metadata context. So we talked a bit about application context. Let's talk about historical context. In particular, you can think of this as a versioning scheme. Okay, obviously data gets versioned. All right, our weblogs may come from over time, and in fact, some data you may update, and so it'll have versions over time based on the way you update it. But we also need to version our code. So if the meaning of data depends on what we do with it, and what we do with it is code that changes over time, then the meaning to track it over time needs to version the code. Right? And the statistical model similarly. So if you have a recommender algorithm that uses code to extract rentals, the parameters and the way that recommender model works are also need to be versioned. Okay? So all three of these things, data, code, and models, have to be in a versioning scheme. And there isn't a single versioning scheme that does this stuff today. Once you have this versioning scheme, I believe we can have intelligent algorithms that will be able to let me say it this way. I want to highlight two different ways that we'll use versions. One is point-in-time kinds of queries, where your algorithms will want to know about a particular version of an object. So for example, if you're doing movie licensing, your Netflix, you have to decide whether to pay money to license a movie for the next year. If the movie was hot in the theater, you want to compare it to similar movies that were hot. But you want to compare it to the state of those movies at the time of their release. You don't want to compare it to where they are today in terms of how are they accessed and who watched them. So then we want to do point-in-time queries on these movies in the past. But we may also want to do trends over time. So we want to do temporal analysis. How does a movie with these features fare over time? So it's not just that we want to be able to do time travel to points in time. We want to be able to take specific objects and track them over time. And those are two different workloads that are difficult to do in traditional data management. So we need systems that store versions that let us do this kind of stuff. Okay. Let's talk about behavioral context. The classic one is data lineage, which is, I say classic, but it's very difficult technically. Data lineage is a very rich area, or data provenance, if you prefer that word. Typical example, we have our data, it's fed into code and a model, and it predicts that I want to rent Dora the Explorer. I cannot abide Dora the Explorer. She's incredibly annoying. And so I want to know why. Why was I given Dora the Explorer? And I need to go back through the models, possibly through the code, even to the data, to be able to answer this question. Okay, so that's data lineage. But data usage is also very useful. So you may have some file in your organization that gets used by different people with different frequencies, right? Similarly for code, right? And similarly for associations of files or associations of files and code and models. We would like to know how people are using it, when they're using it, who knows about what, who's been stuck working on something, who's an expert on something, these kinds of things. Usage can tell us a great deal about what's going on. And here's where I believe that we can really introduce some innovative services into organizations. So you can imagine an algorithm that's living in your data science group, and every once in a while it pops up its head and it taps your analyst on the shoulder and it says, hey, I see you're looking at movie rentals. You should compare that with book sales from last year. There's this data set and perhaps this report that might be relevant to the analysis you're doing. That context, that larger context of what other people have done in the organization, can be something that assists you when you're doing your data science. Right? So that's pretty interesting. How would we build those recommenders? It's like building recommender systems for your data scientists. Right? Here's another example. For people who are sort of your data curators, wouldn't they like to be sort of tapped on the shoulder by an algorithm and told that the guys in logistics check the weather the first Monday of every month? If you're licensing a weather feed from somebody, you better make sure it arrives before Monday and that it's prepped and ready to go for them. Or another example, tap your IT folks on the shoulder. An impact analysis could happen without them asking for it. So for example, somebody changed the Twitter analysis script. You should check the boss's dashboard because the boss likes to see all the tweets that say that he's a genius, and that feed is broken. Right. So these are all examples of things where if you watch usage and you watch the way the data and the code and everything is linked together, you get a much bigger context. So really the biggest context in the organization is all of these things. And we don't currently have tools that take this big picture of how data gets used in an organization and provide a framework for storing that information and APIs for mining it and really utilizing it. So this new world that we've built with new storage layers and new query engines and everything really does need new services. All right, I hope I convinced you of that. And with that, I'm going to hand off to Vikram, who's going to talk to you about Ground.
Thanks, Joe. So before we get started talking about Ground, the actual system we're building at Berkeley, I'd like to spend a second talking about our grounding philosophy, pun very much intended there. So there are a few things that we think are pretty important to keep in mind here. First, we want to start useful and stay useful. We want to provide a useful software artifact out of the box that people can use and will sort of illustrate the value of having a functional data context service, right? Second, we want to stay general. We want to provide an unopinionated view, like Joe was talking about, of data context. We don't want to tell you how you should store or think about your metadata. And the last thing we think is important is designing for scale, right? So to give you an example, usage logs today might be considered data. Tomorrow they might be considered metadata, right? And we don't want to tell you this is data and that's metadata. That's not our job. So we want to be able to support something that can grow very large very quickly, like a usage log. So that being said, this is sort of our view of the world. In the very center here, we have Common Ground, which is our context model, the data model for our context system, as well as a set of APIs to above ground and underground services, which I'll get to in a second. Our context model is what we spent the last few months working on. We've designed a data model that we think is very general, and I'll dive into that in a minute. Underground here, we have the services that we think Ground needs to function well. So scavenging and ingestion, version storage, for example, a few others down there. And the really great thing about this is that there's a bunch of really awesome open source in this space. So for example, for scavenging and ingestion, our friends at LinkedIn have built the Goblin software, which is really awesome. And version storage, there's Git, and there are really cool open source projects in all of these, for all of these boxes underneath. Above ground are a few applications that we think, and this list is by no means exhaustive, but we think that these are some examples of applications that would actually be, able to serve their purpose a lot better if they were to have access to a data context service like Ground. So let's dive into the context model a little bit more. At the bottom of the context model is the meta model, right? The layer that represents the application context to the metadata that Joe was talking about earlier. And here, it's a very simple model. We just have a set of nodes and a set of edges, right? Nodes represent standalone objects, and edges represent relationships. And we think that graphs are, a very mathematically general structure, right? So to prove that to you, let's take a look at a couple common use cases, right, of metadata that we see in the field. There's the relational schema, which can very easily be represented as a graph structure, right? It's just a very shallow, very wide graph where, schemas have tables and tables have columns, and you can represent things like foreign key constraints as relationships between columns. And on the right, we have a JSON document, which again can be represented very generally as a graph. You have contains relationships, and maybe for the lists down below, you have, this element comes after that element. Both of these things are very common things that we'd like to represent, and they can be represented in our metadata layer. Now, we see that every one of these objects really needs to be versioned over time, right? And we want to be able to support that. And it's not just nodes that need to be versioned, but edges, in fact, also need to be versioned to capture both changes to the attributes of the edges and also changes to the edge structures themselves. So we've created a directed acyclic graph, or DAG model, for our versioning system. And DAGs are very powerful mathematically because they actually allow you to represent partial orders. So for example, you can say that the top two items it's very clear to say that the second item came after the first. At the same time, at the third layer, there are the two objects side by side, and we can't say that they came in any particular order. They could have happened at the same time, or one could have happened before the other. We can't say, but we think this is very flexible and it's useful to have such a flexible versioning system. Now the top layer is the usage layer, right? So the behavioral context that Joe mentioned earlier. And so to give you an example of the kind of lineage that we'd like to represent, let's say we have Joe on the left, it's the little person, and there's Dora the Explorer on the right. And just like before, there's a likely to buy or an affinity relationship between Joe and Dora the Explorer. And we want to go back and say, well, where did this relationship come from? So we have a targeting model up there. That's a node in our system. And there's this affinity relationship that's an edge. And there's actually a lineage edge between that model and the relationship that says Joe is likely to buy Dora, right? So the key insight here is that everything can participate in this usage layer. These lineage edges don't just connect nodes to nodes. They can connect nodes to edges or edges to edges or anything, because everything can participate in usage, much like everything is versioned over time. Right? So that's it. That's all that we have in our data model. And we think it's very general, but also very flexible and expressive. Right? So as we've been building this, we've tried to come up with some examples of things that we think validate both the usefulness and the flexibility excuse me, of the common ground model, right? And we also want to have a sort of proof of concept for starting useful. We don't just want to say, hey, this is useful. We actually want to say, here are some examples where this is really useful and we think you should use this. So the two things we've done so far is, first, we've integrated Ground with Git. We're calling that Grit. And we've actually used Ground as a backing store for Hive Metastore, and we're calling that apiary, right? So CS186 at Berkeley is the upper division databases course, right? I first TA'd for it a couple years ago. It was about 100 students. I TA'd for it when Joe was teaching it last spring. It was about 350 students, and now it's 500 students. It's the 6th largest upper division class at Berkeley. And all the CS186 students submit their homework through GitHub, right? Which is pretty cool, but we actually want to be able to do a few things with that. For one thing, we want to be able to track tardiness. So if a student submits their assignment late, we want to be aware of that. Now, if you're a particularly clever Berkeley undergrad, you might know that you can actually go and change the time that a Git commit was created. And that's actually what GitHub will show when you look at the Git repo. So let's say you're submitting your homework 12 hours late, but you go and you change the date, so instead of March 30th, it's March 29th. Then if TA was to go look at the Git repo, it would actually say, oh, the student submitted on March 29th, when that's not true. So we want to keep track of when the commit was pushed so we can prevent this sort of submission time spoofing. And long term, something we'd like to do is analyze some of these homework turn-in patterns to be able to understand how effectively or how quickly students are completing their homeworks, or whether they're completing them at all, and so on. Now, we'd like to do this through GitHub's webhooks APIs, but unfortunately, as we've been building this, we've been having a couple issues. The webhooks API doesn't actually report the full versioning lineage, so we can't rely on GitHub. We need to track the repos ourselves, and it's something we hope might be a point for future collaboration. And for what it's worth, tracking versioning history on Google Docs is much, much messier. Now let's put that aside for a second. We'll come back to it in just a minute. On the Hive side, we understand that Hive Metastore is the de facto catalog, or for metadata catalog for big data, right? Everyone's metadata is in Hive Metastore. But when it comes down to it, Hive Metastore is actually just a relational catalog. And like I was talking about earlier, the relational catalog is just a basic design pattern above our context model, right? It's just a set of nodes and edges. So what we've wanted to do is actually represent all this metadata in Hive Metastore. We wanted to put it in Ground, which we thought would be cool. And now, so we think if you combine apiary with HDFS and Grit, you actually get a fully versioned context store. Now, what do I mean by that? Well, HDFS is cool. It's an append-only file system, and it also allows you to take snapshots of data over time. So we can actually look at old snapshots of data. And with Git, we can also look at older versions of data, right? Which is cool. And then with putting the Hive schemas into Ground, we actually get versioned metadata over time as well. So we can actually go back and look at an older schema that you were using. So as we'll see in a minute, let's say you change your Wrangle script to extract different fields from your raw data, and then you update your schema in Hive. We can actually track that over time, right? So when we combine all these things together, what we really get is time travel, which I can actually show you a demo of now. So let's say we run this query. We run select count distinct URL from weblog.
Can you make that font bigger?
Oh. So weblog is actually just this table that we have that's an external table in Hive, and it represents an Apache weblog that we've wrangled, and we have we're trying to count the number of distinct URLs in this weblog, right? So Hive's doing its thing, and what we're actually going to see in a second when it finishes, we get this number 477 right here, and that's actually a smaller number than we were expecting, right? Maybe we ran this query yesterday and we got a different result, and now we want to try to understand why is this number smaller, right? So let's say we look at the table. And what we actually see is, we have the URL, and then we have the query parameter, which is separated out, which maybe wasn't the case yesterday. So what we want to do is we go to our Git repo, and we see, we actually changed our wrangling script so that we extracted a query parameter from the URL, and we put it in a new field, right? So let's actually, go back in time and we go back in time. But now, remember, since we're changing the number of fields that we're extracting from the raw data, what we also want to be able to do is go back in time with the schema. So one thing we're going to do is we're going to rewind our schema, which is cool. And then the key thing we had to remember after this is that we also were looking at an older version of the data yesterday because weblogs get updated every day. So what we want to do is we want to load an old snapshot of the data, and we're going to say we're going to use the snapshot from March 29th, 2016, yesterday. So we do that. And then now that we've done this, now that we've loaded the old snapshot of the data, we want to make sure we go and we actually we wrangle that data and extract it. And now we're ready to run this again. So if we look at this schema, we actually see now, hey, the weblog is actually, in the weblog table, the query parameter is actually attached to the URL. They aren't separated like they used to be. So now we can run our old query. And what we'll see is that even though we have less data because we used an older snapshot of the data which had fewer entries in the weblog, we'll actually get a bigger number for the number of distinct URLs. Because when you click on a website, let's say on Google Images, if you separate the query parameter out, then it's just images.google.com. But now that we've added the query parameter back in, it's going to be a bigger number, right? We get 845. This is just one kind of cool example of what we think is a useful demo of data context. But at the same time, we also think that there are a bunch of different places where this can be used, which Joe is going to talk about now.
Thanks, Vikram. So part of the fun of taking the alpha software for ground and driving towards a demo today was actually how easy that turned out to be. Right. So we had our versioned meta model for Hive. We put Hive on top of our versioned meta model. The versioning of the schema came for free. It turns out that the way we work with data in HDFS is mostly append only. So the world of kind of big data and gathering data over time kind of gives you versioning almost for free. And then code versioning was an integration problem, right? There is a place to version code. It's called GitHub. So that exercised our goal of making sure that Ground exists in an ecosystem of other tools. And so this was actually a really nice demo because it's rather lightweight. Sort of been beavering away on this for a number of months, but this is not decades of programmer time. But it's possible to start seeing this vision of data context emerge pretty quickly in a fairly light way if you get the sort of simple building blocks right. Okay. And as Vikram said, time travel is just one thing you can do with context. There's so many other things you can do. All right. So I want to talk a little bit about kind of what we're excited about in terms of doing research at Berkeley. Some of the challenges in this space technically. So the focus areas for us, one way to do this is to frame it in terms of our picture of the underground services and the above ground applications. First, we got to get this common ground model right. And so we've been talking to colleagues at a bunch of the different places that have a stake in sort of the big data ecosystem to try to find out what their needs are for metadata. We've been talking to vendors, to customers, to scientists at Berkeley to try to make sure that we are general enough to get this right, and that what we're building also has the function that they need. So it's that balance of simplicity and functionality. And this is, one of these things that you're like, well, how hard could it be? And then you sort of start digging into it, and it's subtle, but it's not fancy when you're done, right? The model that Vikram showed you is deceptively simple, right? And that simplicity is a virtue and something we've come to over time. So once, and this will evolve. Honestly, like the common ground model is something that I hope we'll continue engaging with the community with and lock down over time. It's I think, pretty good starting point. Above ground, there's a few things that I think are exciting to get going on that we're going to be focusing on at Berkeley. The first on the upper right, reproducibility. So our scientific users are very interested in this, and the sort of national funding agencies for science are very interested in scientific reproducibility. And I can give you an anecdote from our friend Saul Perlmutter, who runs the Berkeley Institute for Data Science and is also a Nobel laureate. So Saul has this problem that he has these very expensive instruments measuring the sky, right, telescopes, and they gather terabytes and terabytes of data, and then they run pretty sophisticated algorithms on that data to generate science, right, to generate results. And then they'll find out, 3-4 months later that the telescopes were miscalibrated. So what Saul wants to do is he not only wants to reproduce the experiment, he wants to go back in time and change some of the calibration constants that went into the code and rerun things with those different calibration constants, and then compare how things would have been different if they'd have run it with those calibration constants versus what they'd been assuming was true of the universe for the last 3 months. Right? So this is pretty large amounts of data that he wants to do this versioning on with complicated code. Very interesting context. So I think doing reproducibility in the face of those kinds of issues and complicated software and data is quite fascinating and a big challenge. A second thing that we're focused on, and my colleague is new faculty at Berkeley, Joey Gonzalez. Joey's maybe known to this community as the primary author of GraphLab. Joey's interested in the problem of model serving. So again, let's go back to Netflix. Netflix has recommender systems, right, built in. Those are statistical models. We have lots of tools in the ecosystem for building those models and running them, but we don't really have ecosystem tools for making model serving, that is the daily operation of the end-to-end life cycle of those models, work well. And Joey's interested in how we build efficient, statistically high prediction models in a kind of organized and well-engineered context. So model serving is another place, and versioning and all that stuff plays in there quite a bit. On the left-hand side, parsing and featureization, I think, is just one of those services. It's an application-level service, but it's broadly usable. Data gets dropped into data lakes all the time. What we'd like to have is hooks for people to plug in third-party features up here, third-party code, to do parsing of data and featureization of data. So for example, if I drop in a few terabytes of images into the data lake, wouldn't it be nice if one of you wrote a service that could then generate some metadata and say, here are new images with cats? Right? Or more typically, probably, you might be able to do things like parse CSV files and look for security breaches, right? Oh, I see there's a lot of credit card numbers in this file that just got dropped in the data lake. But you can imagine many of these kind of parsing and featureization features being used two different ways here. Parsing and featureization algorithms kind of being popped in at application layer to interact with data as it arrives and generate metadata. So those are some things I think that are fun on the top. There's many more things. Obviously in the application space, it's whatever you can think of. Underground, while Vikram did say there's wonderful open source across the bottom, I would say a place where it's weak is in version storage. So I think there's a big opportunity, and this is a project I'm interested in making sure happens at Berkeley as ground gets off the ground, in building a database that manages versions over time and never deletes them, that it's very high performance, runs on dense hardware and memory, but that it's keeping the history over all time. And it can do both those point-in-time queries. You can say, what happened 10 years ago? But also can do those over-time queries, say, what's the trend analysis for these things? So this is a challenge that's been put at my feet by some of my colleagues, and I think it's time for the community to think about what's a database look like that really deals with versioning intelligently. And I'll note that it's no coincidence that our meta model has a lot of graphs in it. Graphs are very natural when you look at data lineage and when you look at versions. And so I think this also needs to be a graph query engine or graph database as well. So that's going to be a very interesting, I think, piece of research and hopefully new class of systems that we're going to be focused on at Berkeley, and I'd love to see other people. There are, I would say, two interesting projects in that space today. One is the Datomic product, which is quite interesting from the Clojure people. And then there's a project called Pachyderm.io. And if you're interested in this space, I think we all need to learn more about both of those to the extent that they will share. Pachyderm is open source. Generally, though, my message to prospective graduate students, prospective startup founders, et cetera, is there's so much work to be done here. There's so much room for innovation in this context space. And if we can get our heads out of sort of the narrow focus of some of the projects we've been doing and look at these bigger big data context problems, that is, I think, the final frontier. There's a lot of work to be done. All right, summing up, we're trying to get the community to think about grounding big data with context services 3 kinds of context. Application context, because truth is subjective. It depends on what you're doing with the data. It's no longer just the truth, it's your truth, right? It's your application's truth. Behavioral context, because oftentimes the only way to know what's going on with the data is to see how it's getting used. And then finally, historical context, because as we know, things change. And given how cheap storage is, it's kind of shocking that we haven't been faster to the world of tracking change over time and recording versions. I wanted to acknowledge that we've had conversations with people at a bunch of different organizations, open source groups, companies, who've really helped us out in figuring out what this agenda has been. The warehouse team from LinkedIn, the infrastructure team there, the Navigator team from Cloudera, my friends at Databricks who are building Spark and the Spark Cloud, and then of course my colleagues at Trifacta. And then at Berkeley, folks in the AMP lab who are working on things like cancer genomics and supporting astronomy, and the Project Jupiter team, which is also at Berkeley that does scientific notebooks. We've been getting input from all these folks, mostly because I know them, honestly. And obviously we'd like to broaden the circle and start to get input from more of the community. And as this thing comes out, and we begin to start seeing people trying to use it and breaking it and telling us what we've done wrong, we're looking forward to lots more input. There is a website and a GitHub repo from that website that you can go check out. I will, like any good open source project, we're opening up early, so it's pretty raw. We encourage you to wander through and be in touch with us if you have questions or suggestions for us. Well, thanks for your attention, and we'll take questions. I think we have a little bit of time.
No, we're over.
We're over?
That's how much time we're over.
Oh, we're over. We're out of time. It's been so much fun that we didn't notice. Thank you.